All right. Hi, everybody. We are kind of in the middle of the second exam period, which is due tonight at 8. And then we're also have an assignment set out. So I'm going to slow it down just a little bit. Also, I had a request at the beginning of earlier in the semester to do a few more examples. And so we went through most of chapter 11 in the makeup lecture on Friday. And it really was just an introduction to low cycle fatigue. There are going to be makeup lectures on Fridays for the foreseeable because I think I've postponed like 6 or 8 lectures. So if you were not there, you have not watched it, that's okay. So today's lecture is the example problem at the end of chapter 11. And so I'll walk through it pretty slowly. And there's a really nice discussion at the end of that example problem where they say, well, we solved it this way, but you could also solve it this way. So I'm going to go through and solve it multiple ways, and we'll kind of see how each one affects the answer. And then what we have to consider sort of like in what regime. Okay? So the last lecture was about low cycle fatigue, and we basically came up with a strain versus cycles plot instead of a stress versus cycles plot. Because at those low number of cycles, here, I'll just go to the next slide. At those really low number of cycles, we don't have a stress type situation that we had before. We're doing stress life. Rather, we have something that's more like strain life because it was found that strain cycling corresponds more with the life than does stress cycling. And when you get into very high, let's say, strain amplitudes, right? So if on the y-axis we have something like the change in strain, right? So that could be 0 to some maximum, or that could be a compressive strain to a tensile strain, whatever it might be. Right. When we had very high strain magnitudes, then we get into more of the material properties, right? So we get out of a range where we're using linear elastic fracture mechanics, and we're saying that we can approximate things that way, and we might account for some plastic strains. We might have a plastic zone, but really when we get into the high strain cycling amplitudes or magnitudes, we get out of that regime because there are materials which are, right, strain, let's call it strain strengthening or strain weakening, which means that if we draw the stress strain curve, and I'll show an example of this corresponding to the example problem that we're going to work through. If we look at the stress strain curve for something like 4340 steel, if we have a monotonic increase in behavior, it does something like this. Whoops. Come back. Okay. Where it has a yield point defined kind of around this nose. But if this is a cyclic stress strain curve and we subsequently go to higher and higher strains with each cycle, we find that it follows the linear elastic curve, but then it sort of branches out over this way, right? So we have a cyclic stress strain curve that falls below the monotonic one. And so this is also, I think this is introduced back in chapter, I want to say chapter 8, where we started looking at cyclic loadings like this, maybe chapter 7. I think actually, no, this is figure 814. So we find that the material is not as strong in cyclic loading, especially when you get up to the higher values. And so this would be an example of the 4340 steel of a strain weakening material, which the cyclic stress strain curve falls below the monotonic one. And so this is the reason why we have to consider low cycle fatigue. As I mentioned in the prior lecture, we don't really know what happens at those lower number of cycles and really high stresses on the stress life, that SN diagram. And so we swap over and we start thinking about strains instead. And so if I have a plot where it's number of cycles to failure on the x-axis and then a strain magnitude on the y-axis, we kind of came up with the idea that it was the summary or the summation of two lines. All right, so I'm just going to draw them sort of like that, where one has a lower rate of change than the other, and this is a log-log scale. And so if we sum these two curves, right, then we're going to come up with something like this. Right, up at the top, a continuous function that represents the summation of two types of strains. So one would be the elastic strains, and then one would be the plastic strains. And so if we sum those together, we find that in the very low cycles to failure regime, which has the highest strain magnitude, I'll just draw a plot over here, just draw sort of a line that goes down like this. So if we look at that point, we can see that the plastic strain is higher than the elastic strain, so that dominates in that regime. But when we get out into the higher number of cycles, right, we're still in low cycle fatigue, but we're at a higher number of cycles. We get out here, we're sort of almost to the high cycle fatigue, which we've been studying quite a bit. And so in that regime, the elastic line, the elastic portion dominates. So we really just are saying that the strain amplitude is the sum of an elastic strain amplitude and a plastic strain amplitude. And on a log-log plot, each of those would be represented by a decreasing power law type function. And so each one is kind of a coefficient times the number of cycles to a minus power, right? And then that would give us these decreasing lines here that would sum to sort of a curved line there. So that's kind of the concept that was presented in the last lecture. And so now we're going to use it for an interesting example problem at the end of the chapter. And the reason it's interesting is that it has a component here. It's supposed to last for a grand total of 15 minutes. Okay? So that's a very short time, which means probably low cycle. So we have to look at the fatigue. So I'm just going to read the problem statement here. Suppose that it is desired to design a high-performance, short structural load link for use in an air-to-air missile, where lightweight is of the utmost importance. Okay, so we have to really choose the minimum size on this to reduce mass. The link may be regarded as a two-force member under direct axial loading, P, so that's shown here on the slide, that fluctuates in accordance with the estimate over here in this fluctuation load diagram, loading spectrum. This typical loading block is shown here at the top, so I'll just sort of highlight that up here in green. So it goes out kind of from the lowest point here up to the highest point there, and they say that that corresponds to 5 seconds of loading, or 5 seconds of time. So it's really a very short time. It's more than one, if we count sort of just the peaks in here as a very rough estimate, there's kind of like 8 peaks over the course of 5 seconds. So it's more than 1 cycle per second, so it's more than 1 hertz. Okay, if the material is 4340 steel, 4340 steel, which is heat treated to a specific hardness, and this is, it's not relevant to the problem. It just says that we can use the data from figure 814. And true fracture ductility has been determined to be strain, right, to fracture is this 0.48 value. And this is one of the coefficients in the equation that I just talked about. What size should the cross-sectional area be made to support the load for a design life of 15 minutes? So time is 15 minutes. If a safety factor of 1.2 is desired. Okay. And so we're not going to do the whole rain flow counting, but if we start to think about, okay, what's involved in this problem? Well, there's a few things. The first one is a very short lifetime, so low cycle fatigue. So we're going to use the idea that we can partition the strain out and see, based on this idea of sort of a strain life, what would we expect? And then since we have this loading spectrum, right, we're going to use some sort of cumulative damage. And we also have a non-zero mean stress. So if you look at 0 is here, and I know you can't read all the numbers, and it doesn't really matter yet. But most of those loads are above 0, right? So it's got sort of overall non-zero mean stress. So it has all of these different considerations. So we'll go through them and sort of walk through them systematically. This block that it shows us here is 5 seconds long. So the first thing we can do is just figure out how many blocks we need in 15 minutes, or how many we would expect. Just as a first pass, we don't need any other information from that. So 15 minutes, right, times 60 seconds per minute is 900 seconds. And we have a block that's 5 seconds long. So if we divide that by 5 seconds, then how many blocks we have is 900 divided by 5. I believe that's 180 blocks. So once we get the damage from single block, we can say, okay, multiply that by 180 and see if the thing is going to last based on the dimensions that we have chosen. So the question here says, what size should the cross-sectional area be? And so we are not given that area. All we're given is the loads here. And these loads vary in sort of the thousands of pounds. We can look back at the cyclic stress strain diagram and see, okay, what's the maximum stress that we can possibly put on this thing? And then maybe we'll assign that to this highest region here, right? So we're just going to use that as an example, and then we'll see how we go from there. So let me go forward. Okay. So I put that plot here. I could also just draw it. But this is figure 814A, and it's this cyclic stress strain diagram for 4340, SAE 4340. It has a bunch of magnitudes on there, which I'll talk about in a minute, and all it gives us is really this increment spacing for the X and Y axes. So on the X-axis, it says it's 0.01 inch per inch, and so that's one sort of segment there. And then on the Y-axis, it gives us 50 KSI, which is one segment there. And so if we look up here, then we can get to about 140 KSI in our cyclic stresses before the curve ends, right? That's the end of that curve. So that's what we're going to use at the beginning, and we'll assign it to the highest load there. Okay. All right. So if we do that, the highest, if we go back to the problem statement here, it says that the highest loading is 14,000 pounds. So I'm going to go to this next slide. So P max, 14,000 pounds. And our maximum stress that we're going to use is 140,000 PSI. So you can see that there's a factor of 10, very easy. So the area is the load divided by the stress. So it comes out to be 0.1 inches squared. So we're going to start with that area, because if that's our highest stress, we get sort of almost no cycles at that stress. But we'll get, we have a lot of lower stresses that are going to add up to some damage as well. So that's kind of where we're starting. Okay. So if we take that to be the area, then at every load level, we can calculate what the stress would be, because it's just the loads that were given divided by the area that we've chosen. So in the textbook, they sort of transform the whole rain flow diagram from loads over to stresses based on this area here. And so I'm not going to go through the details of it, but it can be a helpful example. And so here's the kind of rain flow diagram. And so what I really like about this is that they've drawn the magnitudes down below. So for example, if I just show like segment number 1 here, which goes all the way like that, then it shows segment 1 here across all of them, right? So then you can go up and look at the different segments and see that they're all sort of paired up, and that they can represent the spectrum of loading in some fully reversed cycles. So I'm just going to move past that, and then we're going to make some tables on these different segments here and how many. We don't know exactly what order they fall in, but in a single block, it doesn't really matter. We're going to calculate the damage for one whole block because they go in order, and then we'll do another block, another block, another block. Okay, so here's what we have to do now is make a table for the stress reversals. And we had we had 6 of those, so I'm just going to give them numbers like this. And I'm going to write down the magnitudes. So we have maximum stresses and minimum stress for each of these 6 cycles within one block. And these are all going to be in KSI. So I'm going to write down 140, 120, 100, 100, 60, 20, and then minus 60, 20, 80, 0, minus 40, and minus 20. Okay. So we have one that is quite large, the first segment there, and it goes from a maximum stress of 140 to a minimum of minus 60. So it's not fully reversing. It has a mean stress greater than 0. For the second one, we go from maximum of 120 down to 20, so we don't even go to a compressive region at all. Mean stress is greater than 0. Region 3 is similar, but the range is different, both above 0. The fourth type of cycle goes from 100 down to 0, so that's like the type of releasing tensile stress. Segment number 5 goes from positive 60 to negative 40, so also a positive mean stress, only slight in this one, so that's the closest to a fully reversing that we would get. And then we have, well, at a higher magnitude. And then the 6th cycle was really lower amplitude, only 20, but it is fully reversing. So we have a couple that are close to or equal to fully reversing. The other ones all have a strong positive non-zero mean stress. But in this case, we're in low cycle fatigue, and we really are just going to use what we know, which is this stress strain diagram. because we have to translate now these stresses into strains so that we can calculate the fatigue life for for each of these cycles. So I've put some of the levels on this cyclic stress strain diagram that we would need corresponding to these. And I found in the book, this diagram is, I think, I'm going to go like 2 inches high. And so in order to go in there and find distinctions between all of these different values on the y-axis and then look up what are the strains on the x-axis, the book does not give us a very good chart to do that, which is only this one here. So in order to solve this problem in a way that I felt confident, I went ahead and digitized this plot. If you're not familiar with how to do this, you can look up like plot digitizers, and there are like super easy ones in a web browser where you basically drop your picture in, which mine was this picture here, and then you tell it how to scale the x and y axes, and then you literally just click on a bunch of points and it'll tell you the exact coordinates of those points based on how you define your scale in x and y. So if you really want to do that, to understand these things, because these changes in strains are very subtle, then this, I think, is a very good example of when to do that. Okay. Okay, so let's put together now some values of what are these strains, and we are assuming tension, compression, symmetry. Okay, so we are assuming that this is a cyclic stress strain diagram which was created in tension, but also holds for compression. It's not 100% true, but some of those things will be accounted for when we talk about the non-zero strains in a little while. So each of these segments is going to have a corresponding maximum strain and a corresponding minimum strain. So I'm going to write those down here. So the first cycle goes out to almost kind of the maximum, which is like 0.015 on strain. So I had it as 0.0144. And the minimum is minus 60. So it's basically, we look at what it is for 60. So it's kind of this second line that I had. So it's about right here. So it's it's actually negative 0.0021. And then I'll do the same for the rest of them. So for the second one, it's 0.0077. And on the minimum point, it's very, very small. It's like less than 0.001. 0.00065. For the third cycle, 0.00436 or 44, and 0.0029. For the fourth one, we have the same exact value for the third one, and then we go to 0 for the minimum. 60 is corresponding to the same as that negative we had up at the top, so it's 0.021, and then minus 0.0015, and then the last one is those 20s, but it's both positive and negative, so it's 0.00065, and then minus 0.00065. I know I'm writing on top of things. But it's very small strain values, right? So we kind of have to just work in the land of strain here and keep as many digits as we can. So that's why I needed to go to the plot digitizer. If you look at this example in the book, they truncate this at 1 significant digit. And I don't think that's enough, but that's really all you can get from these plots. So that's why I went ahead and digitized it, so I could get a little bit more precision. Okay. Hang on, that's the wrong. Where's my other plot? Sorry. Oh, so now we need the change in strain, right? because our equations that we have for the strain life are a delta sigma, or sorry, delta epsilon, right? It's a change in strain. So I'm going to go to the next slide and write that since I ran out of space here. So for each sort of stress reversal, we had 6 different magnitudes. 6, our delta strain is going to be 0.0166, 0.0070, 0.0015, 0.0044, 0.0036, and 0.0013. So we can really see that all of them are above 0.1%. Some of them are above 0.2%, and then a couple of them go much higher than that, like above, 1%. So reaching pretty high strain values for a ductile metal. Okay, so so how do we go about finding now our cycles to failure? That's what we need next, so that we can see if we go if we know how many cycles to failure, we have one of these cycles in each block, so then we can sum that up and see what our cumulative damage is for that block. The equation that I introduced in the last class said that the strain divided by 2 is equal to sigma prime F divided by 2, divide by E, sorry, modulus. Okay, divide by the modulus times 2 times the cycles to failure to the B power. And then this represents the elastic portion of the whatever strain magnitudes we're applying. And then we sum on to that the plastic strain. So we have a coefficient out here. We have like a fatigue, strain to failure in low cycle fatigue. And then we have our variable here, 2 times NF, and then we put that to the C power. And that represents the plastic portion. And so you can see now that we have a function where we have strain is corresponding to the number of cycles to failure. And so what we need to do now is put in what we know in here, which is we just calculated this delta epsilon. We can look up these material properties, right? Kind of like failure stress in low cycle fatigue. The modulus, these coefficients, because these are material properties, and then the epsilon F. And so once we have those, what we can do then is solve for what are the cycles to failure, right? That would give us the change in strain that we calculated, okay? So there's a few subtleties in here that I'm going to put on the next slide. In calculating sort of B and C, so those can be a function of like a strain hardening exponent, which is given just in the textbook in figure 814. Okay, so what do we know so far? So we know that the fatigue strength, this sort of sigma F, and they sell it sigma F prime. They tell us in the book that we can approximate that as the strain at a fatigue failure in low cycle fatigue. So on that cyclic stress strain diagram, we said we could only go up to 140 KSI. So that's what we're going to assign to that. Okay. We can also, if we want to, look at that stress strain diagram and calculate what the modulus is. So I did that, and that's 28,700 KSI. It's about 200 gigapascals, which doesn't change much for many different types of steels. We are given in the problem this fatigue strain coefficient of 0.48. All right, so they give us that. And then what we need, what's remaining is sort of these exponents, these B and C exponents. We can look up from the table in figure 814b that there's a sort of a strengthening coefficient in cyclic, in a cyclic situation, N prime, which is equal to 0.14. And that's just in a table on that figure. That's all it says. And then we can calculate what we think is B and C from that. So B is minus N prime divided by 1 plus 5N prime. So that comes out to be minus 0.082. That makes sense. This was our power fit for the elastic region. So it's going to be a gentler slope, right, that contributes. And C is similar, but instead of the numerator being minus N, it's just minus 1, and then the denominator is the same, 1 plus 5 times N prime. And so we come up with minus 0.588. Has a stronger power, which makes sense and aligns with what we know. Okay. So we have this sort of complicated expression, which has, which we had over here, where the strain was a function, this strain magnitude is a function of number of cycles to failure, and it's in two different terms with two different exponents, and so it's possible to solve that equation for the number of cycles. But I didn't want to do that because I wanted to keep it with number of cycles sort of always as our independent variable. So what I did instead was I created basically like lookup tables for myself of where I had the number of cycles to failure and then the delta strain value. And I just put in 1 and 2 and 3, and I sort of incremented up to like tens of thousands. Right, past the regime where we would expect this to apply, but I just wanted to see what would happen. And then I calculated the values for the change in strain based on all these inputs, and then I just looked up what was the corresponding number of cycles to failure for each one. So if I go back to my table here, I'm going to write down what I looked up as the cycles to failure. And so for this one, the first value, I looked up, we get 200 cycles of that. Okay, so it's not very many. It's certainly in the low cycle fatigue regime, which makes sense. But it's not just 1 or 2, because even though the maximum tensile goes up to our maximum allowable stress that we even defined, the cycle does not go back to a fully reversing minus 140, right? So our change in strain was not kind of at a maximum. So we can get more than 1 or 2 cycles out of that. We get a couple hundred. For the second one, we get into a lower magnitude. So I calculated like 1368. For this one, I calculated greater than 2 million because the magnitude is just so low. It's like 1.15%. So it's still in the elastic regime, right? So sort of, we go back to mechanics of material, or our materials class, and we say, oh, when did we define yield? Like 0.2% strain, right? So we're below that, so we're kind of still in the elastic regime. So we would expect super high number of cycles. Essentially infinite compared to the other ones. Here, I calculated 5362, 9629, and then the last one also super low, even lower than the other one, so it was like greater than 6 million. Okay. So these are the number of cycles that we could expect to get for each one of these strain magnitudes. And so then what we do is we calculate how much damage we get in one block. So the amount of damage we get in one block is 1, because we only have one of these in each block, divided by that number. So 1 divided by that number, right? We just take the inverse. So this one's kind of like 0.00. I'm going to keep 2 digits here for 7. Then we get into some really low numbers. Then we get 7 times 10 to the minus 4. We get like 4 times 10 to the minus 7. 1, well, kind of like 2 times 10 to the minus 4. 1 times 10 to the minus 4. And then 1 times 10 to the minus 7. So you can see which one is dominating the accumulation of damage. If we sum all of those up, that's the damage that we get in a single block. And it comes out to be 0.0057. Right? And we can do more, we can keep more digits if we want to be more precise. So that's in one block, so that's 5 seconds. We calculated our multiplier way back at the beginning. So if that's our damage for one block, we multiply that by 180 to get the full 15 minutes. And we come up with 1.0251. Right? So this is our cumulative damage number. And Palmgren Minor says if we go above 1, then we would expect failure. So we're really close, but not exact. And we've identified which magnitudes of both stress and strain correspond with the majority of this damage accumulation, which is the one with the biggest strain change, which is that first one we identified up here. Okay, so does that make a lot of sense to everyone? Yeah? Okay, so not too difficult. So this expression that we used up here at the top, which summed the elastic plastic, is based on fully reversing 0 mean stress and 0 mean strain. Okay? And so for some of these, it's very accurate, right? Like for some of these ones down here maybe, because their mean stress is sort of close to 0. It does not really capture some of the other sections, especially the ones with really high mean stresses. And so there is another paper suggested in the text which modifies this expression, sort of this one that we use to solve for the number of cycles to failure, based on the stress ratio of a non-zero mean stress. And so that's how the book solves the problem. So I've just solved the problem sort of a more simple fashion than the example problem. Okay? So we're going to go now and consider what happens if we have non-zero mean stresses. What are we changing? Okay, skip this. Okay. We're going to use the same area, and we're going to run through this. We have the same stresses, right, because we have the same area. But when we get to this part where we're calculating the number of cycles to failure, we have a different expression. And so it's one more step in there, and then we solve for we're going to get a different number on number of cycles to failure. So let me go to the next slide. Okay, yes. So that expression, I'm going to write it down here. It's equation 11.5. And this expression, they literally just took from a single journal paper. And so if you want to look it up in the text, the first author's name is Ohji. The paper is called Cumulative Damage and Effective Mean Strain in Low Cycle Fatigue of a 2024 T351 aluminum alloy. And it's from Journal of Basic Engineering. I don't know what that means. It's published by ASME, and it's from 1966. So there's a lot of improvements that have probably been made on this, but this is just one expression where some researchers have tried to modify what we know to account for non-zero mean strains. I will point out that the last author on this paper's name is Marin, which you will recognize from a lot of our damage accumulation, non-zero mean stress type theories. And so he was one of the originators of a lot of that. And so this is one of his papers. So it builds on a lot of theory that's very well accepted in the literature. Keep in mind that it was done on a 2024 T6 aluminum alloy. And this example problem that we were given is SAE4340 steel. So those have different crystal structure, definitely different microstructure, grains and things like that, and different properties. And so we will want to use this analysis with a grain of salt. But we're still going to use it. There may in fact be expressions in the literature now that are better suited for low cycle fatigue on steels such as SAE4340. I wanted to have an assignment toward the end of the semester where I ask each student to provide an overview and critique of a journal article. And so I'll upload some articles that you can use if you don't want to look up your own. And some of them will be potentially this article or other articles that cite this article so that you can have a nice discussion of how what we've learned in this class is represented in the paper or is not, and you can critique the paper. Okay, so all that context, the expression is the change in strain, delta epsilon, is a numerator and denominator. And the numerator is 2 times 1 minus R, that's the stress ratio, times this strain coefficient, epsilon prime F. And then the denominator is a little bit more involved, so it's got some factors. It still has the cycles to failure NF. We have a coefficient of 4, so that's our first term right there. And then we also have another 1 minus R. And then we're going to bring that up to a power A and sum onto that the number 2 also to the power A, close the brackets, and take all that to the 1 divided by A power. So before we had a stress term and we had B and C and epsilon prime F and modulus. And now we have the stress ratio R, which gives an indication of that non-zero mean stress, and A. And we have our strain coefficient here, and we have an exponent A. Okay, so it's fewer variables, but a more complicated expression. R is the stress ratio. Way back when we started talking about cyclic stresses. And so it's the minimum stress divided by the maximum. And in our case, if we wanted to change the area, that would also be the minimum load divided by the maximum load. So it doesn't change. Okay, depending on, we could go through and iterate with some other cross-sectional areas, and it does not change. Okay, so for every one of our different strain magnitudes, now we have to go through, calculate what R is. And A is related to C, and it's simply the opposite of 1 divided by C. So in this case, it's 1.70 is going to be our power law here, our power exponent. And honestly, I don't know why they define a new variable, because one of the exponents we're working with is 1 over A. So, and it's 1 over C. And so honestly, we could just have this all in terms of C, but here we are. Okay. So let's move forward with that different expression. Okay. So I'm going to have I'm going to keep this in terms of our sections here. So the reversing stress, 1, 2, 3, 4, 5, 6. Our first iteration I'm going to write down the values. So our cycles to failure, if we assume a 0 mean, and we don't account for that, was like 214, 1368, greater than 2 million, 5362, 9629, greater than 6 million, okay? If we calculate R for each of these to represent the non-zero mean stress, the first one is minus 0.43. It's just the minimum divided by maximum. So if the minimum is negative, then R is going to be negative. Then if they're both positive, then R will be positive. Come on. 0.16, 7, 0.8. We had one that went to 0, so R is 0, minus 0.67, and minus 1. So these values can only really range minus 1 to 1. And so if we use that new equation, NF, where we have a non-zero mean explicitly built into the expression, we get some slightly different numbers. 248, 1100, 15,690, 2456, 3292, and 19,065. So if we compare these two columns, you can see that for this high strain, the very first change that we had, we actually can, if we account for the non-zero mean stress, we get a few more cycles out of it. It went from 214 up to 248. So that's the first one. The other ones dropped though, right? And so this one, the second one went from 1368 to 1100. The third one went from 2 million to 15,000. That's a big change, right? So that's a change in a lot of, like 2 orders of magnitude. The fourth one changed by about a factor of 2. The third one changed by about a factor of 3. And then the last one is also very significant. So you can see now that if we account for the non-zero mean stresses or mean strains, we get quite a significant difference. And in this case, a drop in our allowable life, at least for these ones here. But we actually got an increase in life for the first one. So if we add all of that up, we do like sort of 1 divided by those for the non-zero case, right? We get 1.038, and this one was 1.025. Okay, so it's really not that much different in this case because we got a longer life for that first cycle, but then shorter life for all the other ones. Okay, but the ones that we got shorter life for have lower stresses in general, so it's sort of balanced out in this case. I would not expect that to happen for most cases. Okay. So we got values of greater than 1 for both of these, which means that we could actually reduce the size that we chose ever so slightly and then reiterate through. Okay. And then the last slides that I have here are somewhere at the end. There we go. I made a plot of the strain range, delta epsilon, and cycles to failure for these different cases in my from my like sort of lookup table, so I could see what was happening and why these things sort of balanced out. So if we use the expression for zero mean strain, this is what we get. Okay, so this is the sum of those two regimes. I went out to 10 to the 4, which is probably a little too high. We probably want to cut it off at 10 to the 3. And so now the lighter plots on here, those other lines that just showed up, are for stress ratios that are negative. So you kind of have negative to positive, so a little bit more fully reversing. And I found that most of those values fall above the values on the other plot. And so we would get for the same strain range, we would get more cycles to failure. We get a longer life for a lot of these. We can also do that for the positive stress ratios. I know that I'm 1 minute over time. We can also do that for the positive stress ratios, and we can see that it does have a similar trend, except when we get to these really high values here. Then we get a drop in life, not an extension of life. And then I thought it would be fun to plot the equation for not accounting for any non-zero mean strains versus the equation that accounts for them but plugging in r equals 0. So the curves look a little bit different, right? And that could be, yeah, because of a variety of reasons, just the different functional forms of the equations, the fact that it was developed for aluminum, we're applying it to steel, et cetera, et cetera. And the region that they start to deviate is down here in the really high cycles, which doesn't matter because then we would use a different analysis technique anyway. We'd use stress life down there. So that's the whole example. We'll end there and we'll come back on Thursday and probably move to the next chapter. All right, thanks.